Hello, guys. How are you? Hi, everybody. So, welcome to another session of NEET Byte. And today we are going to discuss about the modern physics part 3. Okay. So, guys, Wade sir was about to take this session, but yes. So, actually, he is not available today. So, I'm going to take it up this session. Anyway, so this time Wade sir last time has discussed about the radioactivity, the numericals, and all. So this time we are going to study or discuss about the spectral lines, the hydrogen spectrum, and the Bohr's model. Okay. So this time we are going to take a few numericals on this. So let's just start off. So the first numerical, yeah. Hi everyone. Hi Meghna. Hello Aditi. Hi Prashant. Hello Nisha. Hi everyone. Okay. Good evening to everyone from my side. So, guys, actually, this part is going to be very, very important in this because, like, they may ask you some questions on the Lehman-Balmer series, right? So, you know that in any atom, these are, if you see the spectral lines according to the scientists who have named them. So, this is going to be the Lehman, this is going to be the Balmer, Paschen, bracket, P fun. Okay. So, if from any orbit, let's say n, if it is coming to the 1, so we call the spectral line, we call this one as to be corresponding to the Lehman series. If from the n it is coming to n equals to 2, this is going to be n equals to 1, this is going to be n equals to 2. This refers to the Balmer series. Similarly, for n equals to 3, this is related to the Paschen. So this is how we categorize it, right? Okay, so let's take up this numerical, the ratio of the wavelength of the last line of the Balmer series and the last line to the of the Lehman series. So last line of the Balmer would be from n2 would be infinity to n1 is, this is going for Balmer. Okay, so this is equals to n1 equals to 2, and for the Lehman from n2 equals to infinity to n1 equals to 1. This is for the Lehman, right? So we just need to take the ratio of the two wavelengths, right? So let's just take up this numerical, guys. Just a moment. Let's talk about this one. If you talk the formula, this is for Balmer. So this is going to be rz square 1 upon n1 square minus 1 upon n2 square, right? So this is going to be just a moment. This is going to be 2 square minus 1 upon infinity square, right? So it comes out to be, as this is for, we are taking this one for the hydrogen, or you can take any atom as well, but it should be hydrogen like atom, right? So we are just considering the z equal same in both the cases. So this is 1 by lambda b is equals to r by 4. Consider z is equals to 1 as we are taking hydrogen. Okay, so, and in the case of the bar, this is going to be equation 1. Okay, and if you take about this one, the Lehman one, okay, let me take it up here. So the Lehman would be 1 upon lambda L is equals to rz square 1 upon 1 square minus 1 by infinity square. This is coming out to be r only, as that is equals to 1 here as well. Okay, so this is going to be equation 2nd, right? So what you have to do is you just need to take the ratio. You just need to take the ratio of the two spectral line that is coming out when the electron is jumping from infinity to the 1 and infinity to the 2. Okay, so this you have to calculate. So let me just calculate it here. So this is going to be 1 upon lambda L divide, this is, sorry, 1 upon lambda B to 1 upon lambda L, okay, is going to be what we have calculated. We calculated r by 4 to the r, okay, sorry, okay, r by 4 upon r, right? This we have calculated. So this is going to be 1 upon lambda b lambda L. It's coming out to be r by 4 into 1 by r, right? So this is coming out to be 1 by 4. So lambda L upon lambda b is coming out to be 1 by 4. And in the question, they have asked the same thing. that Balmer, last line of the Balmer and the last line of the Lehman, they have asked the opposite. Okay, they have asked us lambda b ratio lambda l, that is going to be 4:1, right? Right, so this is going to be the answer, guys, and I guess, yeah, the C has to be the answer, right? Any doubt, guys? So these questions are very prevalent, you can say, very prominent as well, because they might give you some excited state or something, and they will ask you about the corresponding lambda. Okay, let's just move on to next one. Yes, now if an electron in a hydrogen atom jumps from third orbit, this is going to be third, to the second orbit, this is going to be the second. Okay, and it emits a photon. So once the electron is jumping, so it is going to emit a photon, h nu, or you can represent as hc by lambda. Okay, the corresponding wavelength is lambda. They have given us the corresponding wavelength is lambda. Okay, when it jumps from fourth to the third orbit, suppose there is a fourth orbit here and it is jumping from fourth to third, so in that case we need to just represent the lambda. Let's take this one is the lambda dash. Okay, so we need to represent the lambda dash in the terms of the lambda, that's all. So how would you take it? So I can write this one as 1 upon lambda is going to be rz square, 1 upon, it is coming from third to the second, right? So this one going to be 2 square minus 3 square. Okay, and it comes out as, just a moment, as z is 1, because it is, we are talking about the hydrogen, so r, so this going to be 4 minus 1 by 9, so it is coming out to be what, 5r upon 36. Okay, so 1 by lambda is coming out to be 5r by 36. So now we'll take it up this one, just a moment. If we talk about the second one, as it is coming from fourth orbit to the third orbit, right? Fourth to third. So this time it is going to be r. Z I have already taken as 1. So this time it is going to be 16 minus 9. Okay. Because, sorry, I have just a moment, guys. It has to be 9 and 16, right? So it has to be 9 and this time it is 16. So this time it is coming out as 7r upon, what would be this, going to be 144, right? So if you take the ratio of these two, so this is going to be 1 upon lambda by 1 upon lambda dash is coming out to be 5r upon 36, 144 upon 7r, r will get cancelled out, and this is going to be how much? Just a moment, it will go right, and this will be, okay, so this is coming out to be lambda dash upon lambda is coming out to be 20, right? And just a moment, just 7 as well, 20 by 7, right? And in the next step you can just take the ratio, you can just solve this ratio. Okay, and lambda dash upon lambda is equals to 20 by 7, and lambda dash coming out to be 20 by 7 into lambda, right? So the second wavelength is 20 by 7 times 20 by 7 times of the initial lambda when it was coming from third to the second orbital state. Okay, so we do have this one again, we do have the C as the answer. Okay, so guys, the only formula you have to remember is this one. This is the Rydberg constant R, you know that, right? And this is a formula you can remember and you can get the questions done. Let's talk about this one. We do have a helium atom, okay, helium plus ion, in fact. Okay, so using the non-relativistic approach, the speed of the electron you have to calculate, and will be, you have to calculate this speed of the electron. And how would you do this? So we do have a helium plus ion. Okay, in this, in the third orbit they are talking about. So if you calculate the energy for the third orbit, and you just need to put it as a, you just need to put it equals to the kinetic energy of that particular orbit, so it will be done. That's all. So what would be the third orbit energy? Energy in the third orbit would be minus 13.6 z square upon n square. Why did I write z square here? Because this time they have taken as helium. Okay, so what would be the energy? This is going to be minus 13.6, minus 13.6 into, helium is going to be 4 2, right? 2 square 4, and this is going to be 3 square, right? And if you solve this one, you just need to put it as, I can see this is going to be in electron volt, so you can just solve this one as 1.6 into 10 power minus 19 joules, to represent in the joules, right? This much of energy you have to put it as the kinetic energy to get the velocity, right? So minus 13.6 into 4 into 1.6 into 10 power minus 19 upon 9 is equals to half mv square. What is m? Mass of the electron into v square. So can you just calculate this long calculation? So this is going to be 13.6, 16.4, 6.4, 9 is equals to this will be 10 power minus 19, 9.1 upon 2. You can bring this down, okay, into v square. So if you solve this one, guys, just a moment. If you are going to solve this one, so v square will be equals to, just a moment, v square will be equals to 13.6, sorry guys, 13.6 into 9, 16.4 into 10 power minus, just a moment, minus 31, 19. How much it would be? Just a moment, upon 9 into 90, 91. Guys, if you solve everything, okay, in this relation, sorry, if you solve everything from here, it will give you this kind of relation. Okay, 13.6 into 16 into 4 into 10 power minus 11 into 2. Okay, and we will come out from here, we will come out from here as 1.46 into 10 power 6 meter per second. Okay, it will give you something this much. Okay, check the calculation, guys, and you guys can just do it by your own. So again, here also the C has to be the correct answer. Okay, okay, so just give me a moment. Yeah, okay, so we do have another one, guys. In this, the electron in the hydrogen atom first jumps from third excited state to the second excited state, and then from second excited to the first excited state. So it is jumping from third to the second one. Okay, and then it is jumping from second to the first one. Okay, so you just need to calculate again the ratio of the wavelength in the two cases, lambda 1 and lambda 2. Okay, I think it is again something on the similar note that we have done initially. How? Okay, so now this is going to be, just a moment, 1 upon the same formula, 1 upon lambda 1 is equals to rz square 1 upon n1 square minus 1 upon n2 square. Okay, and this is going to be, yes, from This is going to be 3 to 2. Third excited to the second, right? So okay, in the next one, it is coming out to be R from second to the first, right? So this one. So in this case, it is coming out 36, the same thing, 5R by 36. In this case, it is coming out to be, sorry, it is coming here, it has to be 4, right? From second to the 1. Okay, so this time 4 and 3R by 4, right? Okay, so guys, just a moment. Actually, just done a bit mistake here. Actually, the excited state is something that you have to take this one. The third is means the fourth. I'm really sorry for that. Okay, I just see whenever excited state is being given to you, you have to take, if it is third excited state, it has to be n equals to 4. Okay, I'm really sorry. This has to be 4 here. This has to be 3. And see, third excited means n equals to 4. Okay, and second excited state means n equals to 3. Okay, and then from second to the first one. Okay, so this you have to take care of it. Okay, this is going to be this one, n equals to 3. So just let me just do it. Okay, so now it is jumping from third to the second, so 4 to 3. So this is going to be 16, sorry, 9 to 16. Here it is 9 and here it is 16, and then again it will be giving you 7R upon 144, right? And this time it is giving to you second to the second excited to the first excited state. So this is going to be 3 to 2. Okay, so here it will be coming out as 4, and here it is 9. So again it will be coming out as 36, and this is going to be 5. Okay, if you take the ratio lambda to 5R, if you take the ratio 1 upon lambda 1 upon 1 upon 1 upon lambda 2, this is going to be lambda 2 upon lambda 1, and it will be 7R upon 144 into 36 upon 5R. So this will be gone, and here it will come out as, right, again it will be somewhere that we have already calculated the similar kind of question actually. So lambda 1 divided by lambda 2 is coming out as 7 by 20. Okay, and they must have asked lambda 1 by lambda 2, right? We have calculated lambda 2 by, just a moment, this is lambda 2 by lambda 1, sorry, just a moment guys. This is lambda 2 by lambda 1, so lambda 1 upon lambda 2 is 20 by 7. Okay, this is going to be the answer. So this time it has to be D. Okay, so the main thing in this question that even I have taken a bit of I have done a bit of mistake as well. So the excited state means whatever the n is given. If it is fifth excited state, you have to take n equals to 6. Of all, every time you just need to add 1 in that, whatever the excited state is given to you. Okay. Okay, so guys, that's all from my side as far as today's YouTube session is concerned. Okay, thank you so much for attending it, and for more information, you guys just check this link. Okay, thank you so much for attending this one. Okay guys, and all the very best for your preparations. Thank you so much. Bye bye, take care.